At 6:57 in the evening Eastern Time on February 1st, 2026, NOAA's GOES-18 satellite recorded an X-ray flux spike of a magnitude that sensors had not registered in the entire preceding year, an X8. 3 class solar flare erupting from a sunspot designated active region 4366, a magnetically complex structure that had grown from near nothing to 14 times the width of the Earth in fewer than 4 days, and in that single eruption released energy equivalent to billions of hydrogen bombs detonating simultaneously in the span of minutes. If you rely on this channel for science grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources, NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the Solar Influences Data Analysis Center in Brussels, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us. But that is not even the complete picture, because the X8.3 flare is not a single event that came and then left. It is the loudest note in a symphony of violence that the sun has been building toward for months, a symphony conducted by a sunspot the size of a small continent, a magnetic structure classified by solar physicists as beta gamma delta, the most dangerous configuration a sunspot can carry. The designation given only when 3 distinct magnetic polarities are simultaneously wound together in a configuration so unstable that energy release is not a question of chance, but a question of timing. The X8.3 was not AR4366's first eruption. It was not its last. And what scientists are now watching as this region continues to evolve is something that carries the unmistakable signature of a sun approaching the peak of its activity cycle, a solar maximum whose intensity has already exceeded the forecasts made just 3 years ago, and which has not yet finished showing what it is capable of. To understand what an X8.3 flare actually is, requires first understanding the scale on which solar flares are measured. The classification system runs from A through B through C through M and up to X, with each letter representing a tenfold increase in energy output. An A-class flare is barely a whisper. A C-class flare can disturb radio communications briefly and then pass. An M-class flare, the kind that would be front-page news in a quieter year, carries enough energy to disrupt high-frequency radio across the sunlit half of the Earth for minutes at a time. An X-class flare is something categorically different. And within the X-class, the numerical suffix matters enormously. X1 is powerful, X5 is historically rare, and X8 sits at a level that only a handful of events in the modern era of satellite monitoring have ever reached. Within the X-class itself, each unit of increase is not a small step. It represents a significant multiplication of energy. An X8.3 is not merely a large flare. It is one of the most energetically extreme events our star is capable of producing while remaining within the bounds of what the current solar cycle has so far generated. The sun, in other words, reached deep on February 1st, 2026. It reached very deep. What the official data from NOAA and the Solar Influences Data Analysis Center, known as SIDC, actually shows is that AR4366 did not simply produce the X8.3 and stop. In a 24-hour window beginning late on February 1st, the region generated at least 18 M-class flares and 3 X-class flares in rapid succession. SIDC classified the sunspot group simultaneously under their own designation, Sunspot Group 784, and confirmed by February 3rd that the region had grown to approximately 14 times the width of the Earth in area, with its magnetic field structure described as not merely complex, but as actively reconfiguring. The magnetic field lines inside AR4366 were twisting, reconnecting, and releasing energy in waves. Space Weather, COM, which aggregates real-time solar monitoring data, described the region at peak activity as a solar flare factory, a phrase that in the context of space weather science is not hyperbole but documentation. A factory implies continuous production. That is exactly what the instruments recorded. And here is where this account becomes genuinely significant. The X8. 3 flare reached Earth's upper atmosphere at the speed of light. 8 minutes after detonation, the electromagnetic radiation arrived. It slammed into the ionosphere, the thin, electrically charged shell of atmosphere that sits between roughly 60 and 1,000 kilometers above the surface of the planet, and it caused an immediate R3 level radio blackout, severe by NOAA's own classification scale. High-frequency communications across the South Pacific were disrupted. Pilots flying polar routes over the Pacific and Indian Oceans found their high-frequency radio communications degraded or interrupted entirely. Ham radio operators across Australia and New Zealand watched their signals fade. GPS receivers across Europe and North America registered brief positional errors as the flare's X-ray burst distorted the ionospheric layer through which GPS signals must travel to reach the ground. NOAA's radiation storm monitoring triggered S3 level alerts. Satellite operators around the world, including teams at the European Space Agency and Japan's JAXA, activated protective standby protocols for spacecraft in low Earth orbit, shielding sensitive electronics from the incoming particle radiation that X-class flares carry in their wake. Think for a moment about what GPS disruption actually means at the scale of daily life in 2026. It is not simply that a navigation app shows the wrong street. Precision agriculture across millions of hectares of farmland in Australia, the United States, and Southeast Asia depends on GPS accuracy at the centimeter scale to guide autonomous tractors and calibrate irrigation systems. Container shipping across the Pacific relies on GPS positioning for port approach and channel navigation. Commercial aviation uses GPS as a primary navigation aid across oceanic routes where no radar coverage exists. Financial trading systems use GPS-derived timestamps to synchronize transactions to the microsecond. When the ionosphere is disturbed by X-ray flux at X8 intensity, the signal degradation cascades through every one of these systems simultaneously. The disruption from the February 1st flare lasted approximately 1 hour at peak intensity. 1 hour is not a catastrophe. But the system is not inactive, it is accumulating, and the next eruption from AR4366 came within hours. The CME, the coronal mass ejection, that accompanied the X8. 3 flare did not travel directly toward Earth. NASA's solar modeling showed the plasma cloud departing the Sun at an oblique angle, its trajectory carrying the bulk of the ejected material northward of the Sun-Earth line. This was not good fortune in any celebratory sense. It was the narrow margin that separated a minor geomagnetic disturbance from something considerably more consequential. When the CME's leading edge finally arrived at Earth's magnetosphere on February 4th and 5, SIDC confirmed that it produced a KP index reading of 5, a minor geomagnetic storm, classified G1 on NOAA's 5-point scale. A glancing blow. The magnetic field embedded in the plasma cloud brushed the outer edges of Earth's magnetosphere and produced a brief episode of enhanced geomagnetic activity, with aurora potentially visible at high latitudes before diminishing. The monitoring was in place and detection was possible, but the outcome depended entirely on a trajectory calculated by instruments, not guaranteed by physics. Had the CME launched at an angle 15 degrees closer to the Sun-Earth line, the modeling would have told a different story. On February 4th, before the CME from the X8.3 even finished delivering its glancing impact, AR4366 fired again. An X4. 2 flare erupted at 12:13 UTC, confirmed by NOAA's Space Weather Prediction Center in a public bulletin, timestamped 14:20 UTC the same day, the X4. 2 caused radio blackouts across Africa and parts of Europe. Then on February 5th, the region produced an X8. 1 eruption, the third most powerful flare of solar cycle 25 to that date, according to data from the Watchers, a space weather monitoring publication. The region that solar physicists had spent 3 days watching had produced, in 5 days, flares of X1, 0, X8, 3, X4, 2, and X8. 1 magnitude, alongside dozens of M-class eruptions that in any quieter period of solar activity would each have been the most significant event of their respective weeks. The question is not whether this level of activity is significant. The question is whether the infrastructure of a civilization that has spent 40 years becoming entirely dependent on space-based systems has been built to withstand it. And this is where the historical record must be brought to bear. Because what is happening now is not speculation. It has already happened before. The geological record holds the evidence. The documentary record holds the evidence. And the evidence dates to the morning of September 1st, 1859. On that morning, an English amateur astronomer named Richard Carrington was sketching sunspots in his observatory in Redhill near London when he witnessed something that no human being had ever described before. A sudden, intense flash of white light erupting from the surface of the sun, lasting approximately 5 minutes before fading. Carrington noted the event carefully, combined his observation with that of independent witness Richard Hodgson, and published both accounts in the monthly notices of the Royal Astronomical Society, the first recorded observation of a solar flare in human history. What followed in the next 17.5 hours redefined the boundary of what the sun is capable of delivering to a populated planet. The coronal mass ejection that accompanied Carrington's white light flare crossed the 150 million kilometers between the sun and Earth in 17.5 hours. A transit time so brief that modern space weather scientists, who routinely calculate CME arrivals in terms of 2 to 4 days, initially found it difficult to accept. By contrast, an ordinary CME takes approximately 3 days to make the same journey. The Carrington CME arrived at roughly 8 times the speed of a typical event. When it struck Earth's magnetosphere, it produced the most intense geomagnetic storm in recorded human history. Aurora Borealis was observed as far south as the Caribbean and Central America. In Australia, gold miners camped in the outback woke in the middle of the night believing it was dawn because the aurora glowing in the southern sky was bright enough to read by. Telegraph systems across Europe and North America failed catastrophically. Operators were shocked by electrical currents surging through their equipment. Some telegraph offices caught fire. In a deeply instructive historical detail, certain telegraph operators found they could continue transmitting messages with the battery power disconnected entirely. The geomagnetically induced currents running through the wires were sufficient to carry the signal. Recent scientific estimates place the Carrington flare's magnitude at approximately X45, though estimates have ranged as high as X80. The X8.3 from AR4366 was not a Carrington event, but it is a verified, documented reminder that the Sun produces events on a scale that makes X8 look moderate by comparison, and that what AR4366 delivered in February 2026 exists on the same continuum as what Richard Carrington sketched in his observatory notebook 167 years ago. This is not a hypothesis. This is documented in the geological record. Ice cores drilled from Greenland and Antarctica contain preserved chemical signatures of ancient solar proton events. Layers of beryllium-10 and chlorine-36 deposited by cosmic rays during periods of extreme solar activity. One such layer, dated to approximately 774 to 775 AD, represents a solar particle event estimated to be between 10 and 100 times more energetic than anything recorded in the modern instrumental era. The event, now known in the scientific literature as the Miyake event after the Japanese researcher who identified it, produced no written record of disaster, because no civilization in 775 AD possessed the electrical infrastructure that solar storms require in order to translate their energy into human catastrophe. We do. In 2026, humanity operates approximately 9,000 active satellites in Earth orbit. We operate high-voltage power transmission grids spanning hundreds of thousands of kilometers across every inhabited continent. We operate 5G and satellite-based communications networks on which emergency response, financial systems, weather forecasting, and military coordination all depend simultaneously. The question is not whether a sufficient solar event could disrupt all of these systems at once. The instruments already showed a preview of the answer on February 1st. The question is when the event capable of delivering that disruption at full scale will occur. Now bring this back to the human scale, because the people living closest to the consequences of severe space weather are not the engineers at NOAA's Space Weather Prediction Center in Boulder, Colorado, or the satellite operations teams in Toulouse or Tokyo. They are the 400,000 residents of Anchorage, Alaska, who live beneath polar flight corridors where radio communication blackouts from X-class flares can leave commercial aircraft without reliable and high-frequency contact with air traffic control during the hours when GPS distortion and radio silence overlap. They are the farmers in the Murray-Darling Basin of southeastern Australia, one of the most agriculturally productive regions on Earth, where precision GPS-guided irrigation systems manage water distribution across 2 million square kilometers of farmland during a period when water availability is already stressed by climate-driven drought patterns. What would those farmers ask if they could look at the NOAA alert logs from February 1? They would ask how long the disruption lasted. They got lucky with 1 hour. The question is, what happens? The hour their planting season's timing window aligns with an event at X8 intensity that is accompanied not by a glancing CME, but by a direct one. The system is not inactive, it is accumulating, and the accumulation is connected to forces that extend well beyond the sunspot that triggered February's event. Solar cycle 25, the current 11-year cycle of solar activity measured from solar minimum to solar maximum and back again, was initially forecast by a panel of NASA and NOAA experts in 2019 to be a moderate cycle, likely no stronger than cycle 24, which was itself the weakest cycle in a century. That forecast has not survived contact with the data. Solar cycle 25 has significantly exceeded projections. The Solar Influences Data Analysis Center and the Royal Observatory of Belgium have both confirmed through their international sunspot number tracking that cycle 25 reached monthly sunspot counts in 2024 and 2025 that surpassed the official forecast maximum by a measurable margin. The October 2024 solar maximum, as reported by NOAA and confirmed by independent solar observatories, marked the peak of the cycle. But solar maxima are not a single moment. They are a plateau. The sun does not reach peak activity, fire its biggest flare, and then immediately decline. It remains near maximum activity for months, sometimes more than a year, with intense sunspot regions continuing to emerge during what climate cosmos? Comms space weather coverage described as the sun's sprint to mid-2026 maximum. AR4366 emerged during the sustained plateau, and it emerged with a magnetic configuration that solar physicists described in precise technical language, beta gamma delta. That language is itself the warning. Scientists choose their language carefully here, and that careful language carries a precise meaning, a sunspot region that carries not 2, but 3 distinct magnetic polarities in direct proximity, where the field lines separating opposite polarities are so compressed and tangled that reconnection events, or the explosive release of stored magnetic energy, can cascade through the region in rapid succession rather than a single discharge. This is why AR4366 produced not 1 X-class flare, but 5 X-class flares in 5 days. The energy had been stored across 3 interlocked magnetic systems. Each eruption did not drain the region's capacity entirely. It rearranged the field lines and created new configurations for subsequent discharge. There's a second connected system that demands attention here, and it operates at a scale most space weather coverage overlooks entirely. The thermosphere, the uppermost layer of Earth's atmosphere, sitting between approximately 90 and 500 kilometers altitude, expands when solar activity is high. The extreme ultraviolet radiation and X-ray flux from X-class flares deposits energy into the thermosphere, heating it and causing it to swell outward. The consequence of thermospheric expansion is directly measurable. Satellites in low Earth orbit experience increased atmospheric drag. At the altitudes where most remote sensing satellites and low Earth orbit communications constellations operate, roughly 300 to 600 kilometers, even a subtle expansion of the thermosphere increases the density of the residual atmosphere enough to accelerate orbital decay. Space weather. COM's Thermosphere Climate Index, updated daily, showed elevated readings throughout the period of AR4366's peak activity. This means that every satellite in low Earth orbit, including the hundreds of satellites operated by commercial broadband constellations that now form the backbone, internet access across large portions of the developing world, was experiencing elevated drag during the period when AR4366 was active. Operators compensate for this by conducting more frequent orbital maintenance burns, expending propellant reserves that were budgeted for the satellite's full operational lifespan. The effect of sustained solar maximum on low Earth orbit satellite lifespans is documented and measurable. Solar cycle 25 is shortening them. And here is the third system, one that the long view of solar science reveals when the data from ground-based magnetometers is placed alongside the space weather record. Earth's own magnetic field is not constant. It has been weakening measurably over the past 2 centuries, with the rate of weakening accelerating in recent decades, according to data from the European Space Agency's Swarm satellite constellation. The South Atlantic anomaly, a region of significantly reduced magnetic field strength centered over South America and the South Atlantic Ocean, has been expanding and deepening. This matters in the context of AR4366 because Earth's magnetic field is the first line of defense against solar particle radiation. A weaker field means that the shielding it provides against energetic particles ejected during solar flares and CMEs is less effective across a larger geographic area. When the next X8 class or larger flare arrives with a CME traveling directly toward Earth rather than at a glancing angle, the interaction between an energetically reduced magnetosphere and a full-force solar plasma cloud will produce stronger geomagnetic storm conditions than the same event would have generated a century ago. The system the Earth has used to defend against space weather for 4 billion years is itself in a period of change, and the Sun has chosen this particular moment in that change to exceed its own forecast. Think of the roughly 3 million people living in Auckland, New Zealand. On February 1st, 2026, Auckland was on the sunlit side of the Earth when the X8.3 flare peaked. High-frequency radio blackouts confirmed by NOAA's data fell precisely over the South Pacific, including the airspace and maritime corridors that connect New Zealand to the rest of the world. Auckland's electricity grid is modern and well-maintained. Its satellite communications infrastructure is robust. And on February 1st, nothing catastrophic happened there. People woke up and went to work. The ferry ran across Waitemata Harbor. Air New Zealand flights departed and arrived on schedule. What the people of Auckland did not see, because there was nothing to see with the naked eye, was the invisible X-ray pulse that spent 8 minutes crossing 150 million kilometers of space, then spent 1 hour depositing its energy into the ionosphere above their city, degrading the radio environment that their pilots, their maritime operators, their emergency dispatchers, and their GPS-dependent precision industries all depend on, and did so silently without warning, without a visible flash in the sky, without any sensation whatsoever at ground level. What those people would ask, if they had access to the instruments that recorded it in real time, is a question that space weather scientists have been asking for 40 years. They would ask, what if the next one is bigger? What if the next one comes directly? Scientists at NOAA, NASA, and the SIDC have been clear in their public communications about the limits of current forecasting capability, and that clarity is deeply instructive. The monitoring is in place and detection is possible, but prediction, true advanced prediction of when a specific sunspot will produce an eruption of specific magnitude, remains outside the reach of even the most sophisticated solar physics models currently operating. The instruments can tell us that a sunspot carries a beta-gamma-delta magnetic configuration, and that classification carries a statistically elevated probability of X-class flaring. They cannot tell us whether that flare will come in the next hour or the next week. They cannot tell us with certainty whether the associated CME will travel toward Earth or miss by a wide margin. And they cannot, with the current state of the science, tell us whether the Earth-facing CME they are tracking will arrive with its magnetic field oriented southward, the orientation that most efficiently couples with Earth's magnetosphere to drive the deepest geomagnetic storms, or northward, where the coupling is weak and the storm remains minor. These are not failures of the scientists operating the instruments. They are honest statements of the boundaries of a young science working with a star that has been burning for 6 billion years and has no obligation to be predictable. This has already happened once at scale beyond X8, and the record of it is still preserved in the geological record, in the ice cores, in the magnetometer logs, in the singed wiring of telegraph offices that stood in cities that no longer use telegraph. The record is unambiguous. The sun produces events of extreme magnitude on timescales that are short relative to the history of industrial civilization, but long relative to any individual human awareness of the threat. The 1989 geomagnetic storm, verified by NOAA historical records, classified as a G5 event, knocked out power across large sections of the province of Quebec within 90 seconds of the CME's impact on the magnetosphere, leaving 6 million people without electricity for approximately 9 hours and causing damage to power grid transformers that required months of repair. That storm was produced by a flare estimated at X15. The March 1989 event remains the most economically damaging space weather incident in the modern power grid era. AR4366's X8.3 was not a March 1989 event. But the range between X8.3 and X15 is a range that a single active sunspot region, under the right magnetic conditions, can traverse in a single additional eruption. The question is not whether a solar flare of sufficient magnitude to produce a G5 geomagnetic storm will occur again. The geological record, the historical record, and the current behavior of the sun in the sustained plateau of solar cycle 25 maximum all point to the same conclusion. The question is whether the power grids, satellite constellations, GPS networks, aviation communication systems, and financial infrastructure of a civilization that did not exist during the Carrington event and was just beginning to electrify during the 1989 Quebec storm are prepared to absorb what that event will deliver when it arrives. The Lloyd's of London risk analysis published in the aftermath of the May 2024 G5 storm estimated that a Carrington-class event striking Earth today could cause between 0, 6, and 2. $6 trillion in economic damage in the first year alone, with full restoration of damaged high-voltage transformers requiring between 4 and 10 years. Because the specialized transformers that form the backbone of high-voltage power transmission are not manufactured in large quantities, are custom-built for specific grid configurations, and cannot be rapidly replaced. Minutes are not hours, and hours are not days, and in this context, the difference between a 1-hour radio blackout from an X8.3 and a multi-day power grid disruption from a direct CME at Carrington intensity is not a difference of scale. It is a difference of civilization. AR4366 continued rotating across the solar disk after its most intense period of activity, and as it rotated toward the western limb of the sun in the days following February 5th, the character of its eruptions changed rather than stopped. The region produced additional M-class flares confirmed by NOAA's Space Weather Prediction Center bulletins through mid-February, demonstrating what solar physicists mean when they say that a beta-gamma-delta region is not spent by producing X-class flares. It is rearranged. The magnetic field lines reconnect into new configurations, each new configuration carrying its own potential energy reservoir. SIDC's bulletin confirmed that, even at reduced intensity, the region retained its structural complexity and its capacity for further strong eruptions. This is not a sunspot that exploded and fell quiet. This is a sunspot that introduced itself. What the official data actually shows, when taken in full, the NOAA alert logs, the SIDC bulletins, the NASA Solar Dynamics Observatory imagery, the GOES-18 X-ray flux records, the real-time thermosphere monitoring on space weather, is a sun that is currently operating near or at the upper end of what solar cycle 25 has produced, in a sustained maximum phase that has already exceeded initial forecasts. with active regions capable of producing multiple X-class eruptions in rapid succession emerging from a solar disk that is not finished with its current activity cycle. The monitoring infrastructure built over the past 4 decades, GOES weather satellites, NASA's Solar Dynamics Observatory, the Solar Orbiter jointly operated by ESA and NASA, India's Aditya L1 spacecraft positioned at the Sun-Earth Lagrange, 1.5 million kilometers from Earth, can detect and track these events as they happen. The warning times for CME impacts range from approximately 15 minutes to several days, depending on the speed of the ejection and the precision of the directional modeling. For the most extreme, fastest CMEs, the Carrington-class events that cross the Sun-Earth distance in 17 hours, rather than the typical 72, that window contracts sharply. 15 minutes is not enough time to shut down a power grid in a controlled manner. It is not enough time to safe mode every satellite in a low Earth orbit constellation. It is barely enough time to confirm the alert has been received. The sun has been burning for 6 billion years. For the first 5.99999 billion of those years, no species on this planet had built anything that a solar flare could destroy. The civilization that has built those things has been operating its most vulnerable infrastructure. The high-voltage power grid, the satellite constellation, the GPS network, for fewer than 80 years. In the context of solar time, 80 years is less than the blink of an eye. The sun has not changed. The sun is doing exactly what the sun has always done. What changed is what we built in its path, and what we have not yet finished making resilient enough to absorb what the star at the center of our solar system has already proven in the verified geological record, in the ice cores of Greenland, in the telegraph logs of 1859, and in the NOAA alert bulletins of February 1st, 2026, that it is fully capable of delivering, and what active region, 43 skitsks, 14 times the width of the Earth. Beta Gamma Delta, the most dangerous magnetic classification a sunspot can carry, delivered as a demonstration, as a measured preview, as a fact now recorded in the instruments and preserved in the data on a winter evening when most of the people living in the path of its radiation were asleep.